Now recall that the Asen-Schoenberg-Whitney theorem tells us that a polynomial has only real zeros if a certain infinite matrix is totally non-negative. That's something that you can't program into a computer because there's infinitely many minors to check. And it's possible to show that there exists no finite subset of the minors that would be sufficient to check. So it really is an infinite test. And maybe you could guess a planar network which has path matrix equal to that infinite Toeplitz matrix, but maybe you can't. Now, Gantmacher's theorem is a finite test. This is something you could program a computer to do. So it's a finite test to see if a polynomial has only real zeros or not. On the other hand, I don't think anybody's ever used it because it involves a totally non-negative matrix, but there's no very nice planar network that goes along with it. So I'm going to show you just so that you know that there's a finite test, but I don't expect you to ever use it. So the theorem due to Gantmacher in 59 says, let's let a of z be 1 plus a1z plus a2z squared, etc. Let's say it's a degree d polynomial, a d z to the d. Let's say it factors as 1 plus alpha I z, product as I goes from 1 to d. And this polynomial has only real and distinct zeros. If and only if the following matrix is totally non-negative, actually totally positive. If and only if the matrix, we have a D, and then power sums here, P1, and then more power sums here. The first row has, it's a D by D matrix, so we go up to the D minus first power sum. And these power sums are all on diagonal stripes. And the biggest power sum here is the 2D minus second power sum. If and only if this matrix is totally positive. So that is, all the minors are strictly positive. Strictly greater than 0. So one nice thing about this theorem, as I said, is that it's a finite theorem. So we could conceivably test all of the minors here for positivity, and if they're all positive, then yes, the matrix has only real zeros, and in fact they're all distinct. I suspect that the polynomial has only real zeros, which are not necessarily distinct, if and only if this matrix is totally non-negative. But I haven't seen that in writing, so I'm not positive, but I think that's true. So some things to know about this. It actually is sufficient to test the matrix to see if it's positive definite for positive definiteness, I guess. This matrix is positive definite if and only if it's totally positive. Another fact is it is V transpose V, where V is the Vandermonde matrix. So V equals, we've got all ones in the first row, and then variables, actually I guess alpha, alpha 1, alpha 2, up to alpha n in the second row, and then they're raised to different powers all the way up to the d minus first power. Now if alpha 1 through alpha n are all real and distinct, actually these are d because there's d of them. Alpha 1 through alpha d are real and distinct, then the Vandermonde matrix is totally positive. Its transpose is totally positive, and actually I got this transpose wrong. If this is V, then the Gantmacher matrix is V times V transpose. So if these numbers are all real and distinct, then V is totally positive. I know a planar network, but it's sort of messy and I'm not going to bother making you guys look at it. You can show this by induction. Another fact is that the determinant of V is the product of all the differences of these numbers. Therefore, the determinant of the transpose is the same thing, and then the determinant of the matrix times its transpose is the product of all squared differences of these numbers. So this is the discriminant of the polynomial a of z. So again, I don't anticipate that we're going to use this theorem, but I want you to know that there is a finite test, and that's enough for this week.